This video will move into section 2.2. We'll continue talking about the derivative, and basically this section kind of serves as a lot of really good reminders about how the derivative acts as a function. We've already started to introduce this. 2.1, we gave the definition of the derivative. We introduced a little bit of notation, the concept of the derivative, giving the values for the slope of the tangent line. But then we realized even in that video, we can do better. Instead of always trying to find the slope at every single individual spot, why not find a derivative function, and then we could use that function no matter what the x-coordinate is. So we've already established that, and that's the difference between f prime of a, which specifically is the derivative of f of x at x equals a, and specifically, what does this value give us? This is literally how we're translating it. So the input is this x value a. The output is that this gives us the slope of the line tangent to the original curve f of x at x equals a. So that's how we began. And again, we always started off already having that x-coordinate a. But doing it generically and finding f prime of x, again, as a function, regular f of x, input an x value, output a y, but now you're still inputting an x, but the output is again that slope of the tangent line. And like I was just saying a moment ago, instead of needing f prime of 2, so using the formula with 2, and then needing f prime of 3, and using the same formula again with a is 3, that if we just found f prime of x, and then we could use this function with any x value, with x is 2, with x is 3, and we could keep going. So that's what we've established so far. But now, taking that a little further, you notice I already have a question written up here. What does it mean to say f of x is differentiable? We established that we've got an original function f. F prime would be the first derivative of this function f. But now, what does that mean to say this is differentiable? What that means essentially is that f prime has a value. If there is a value for the derivative at that particular x-coordinate, then your original function f is differentiable at that x-coordinate. But that sounds like I'm just talking in circles, but what we really need to realize is now applying. What does that really mean? What does it mean that f prime has a value for all the x's, for all the a values that we can pick, and what does that tell us about the original function f? So what this really tells us, all these slopes of the tangent lines, if my function is differentiable, if there are values for the derivative, then what that actually ends up giving us is a graphing property. And this is a little similar to the idea of continuity. Continuity has a whole formal definition, but looking at it as a graphing property, the function is continuous wherever it is connected, and discontinuous, has discontinuities at the points where the graph is disconnected. And we could do something very similar with the idea of differentiable. F of x is differentiable. Like I said, literally it would be if f prime exists for that given x coordinate. But what that translates to, and this is informal here, this function is differentiable if the graph of f of x is smooth. But now again, this is an informal term. What do I mean by saying that the graph is smooth? I'm saying that there are no breaks, gaps, or sharp edges. I normally call these sharp points. No sharp edges in our graph. That's what we're talking about here. So really quickly, again, that's an informal term, but very quickly, now that we have the graph of f, we can apply this concept. So that if I just give you a quick generic version here's a graph, f of x, and I'm not even going to label my y-axis. And if my graph does something like this, again, what does it actually mean to say f of x is differentiable? Or if the question is, where is f of x differentiable? Where does it have a derivative? Well, a couple of quick things. You can't have a derivative if there is no point. So this open hole, and even if this had a filled-in point elsewhere, but this open hole, how can you draw a tangent line to the curve if there is no point there? And same thing here. Over here, this goofy spot, how are you supposed to draw a tangent line? Again, we need the idea of what's happening on both sides of the line when the graph doesn't come together. So we're actually getting, the book writes this as a formal property, but we'll just write this quickly as a little aside. If my function is differentiable, well, one of the first things, the function must have already been continuous. That you can't even draw tangent lines to consider the slope if you already have breaks and jumps. One other very quick thing, we talked about if and only ifs a little bit back and how those are both directional statements. This is one-sided. You get this result, if this is true, then this is a result we can count on. If we know the function is differentiable, then I know that same original function was already continuous. It does not go the other way. If the function is continuous, that does not imply that the function is differentiable. But, so we can't reverse the statement, that's not true, but we can reverse and negate. This is formally called the contrapositive. Negate the conclusion, then that leads to a negation of the assumption. So if the function is not continuous, then the original function is not differentiable. So that's one of my first points to make here. That idea of no breaks. If we already have breaks, jumps, gaps, these 3x coordinates, x is 1, x is 3, and x is 4, these would all be classified as discontinuities, and therefore there is not even a question about is the function differentiable here. It is not. One other quick point just to make before we keep going in this chapter, you really need to start embracing the full notation. And a part of that is not using the word it. When people say things like, if it is differentiable, then it is continuous, you got to be very clear what the it is. At least in this case, it's the same it in both of these. You're talking about the original function f of x, but little things. Later, we're going to start having theorems that connect the original function f to the derivative f prime. So you got to be very careful when you're referring to the original function versus when you're referring to the derivative. So I just wanted to say that now, to make sure as we're taking our notes and as we're reading and thinking that we're already not using shortcuts that are going to get us in trouble later on. So, little practice in logic, seeing a little bit more about how statements work, what's true, what's not. This statement only leads to this conclusion. I can't reverse it. And we're already getting our first big picture. How are we going to figure out where f is differentiable? We're going to treat this very similar to continuity. We're going to look and say, where is it not differentiable? And then it is differentiable everywhere else. So from what I've done, I've already established that the function, this graph, is not differentiable at these 3 points. Those are the breaks, the gaps, the discontinuities that automatically lead to our function not being differentiable. But the second thing here is this idea of a sharp point. Do you see a sharp point on my graph? I'm talking about this. Now, a sharp point doesn't always have to go up like this, could go up like this, it can go down like this, but those are our two most common examples of sharp points. We could also have some situations with piecewise functions where you're going from one definition to another, but at that exact point, even if they meet at that exact point, there still is a little bit of a hard edge. That's what I'm referring to as sharp points. And that's what, going back to my original statement here, not having these sharp points, these sharp edges, that's what we're talking about when we say our graph is smooth, that everything is free flowing and doesn't have these features. So very quickly, we'll come back and finish this question with this in just one moment, but to look at something, another example. That is a common graph for a polynomial, a little bit more of a friendly function that we're a little more familiar with. I don't care exactly what this function is. It's probably like an x cubed type function based on the two spots and the end behavior and other things, but that's not the point. The point is that a lot of our functions have a lot of these good properties. That a polynomial, we've already pointed out that polynomials are always continuous everywhere. There's no breaks or holes. But secondly, polynomials also are always smooth. That when you're going to peaks and valleys, that you do so in a smooth, round fashion, not in these hard, sharp, pointy fashions. So that's what I'm talking about when I say sharp points. If I said, where is G differentiable? The answer is everywhere. There are no discontinuities, there are no sharp points, so there's nothing to throw out. This would be differentiable from negative to positive infinity. Come back up here. Well, where is this differentiable? We threw out these spots. These are not differentiable. Again, you can't draw a tangent line at any of these spots. And if you really tried to force it here, this is the sharp point, so we're going to throw this one out as well. But if you really tried to force it, what's happening to the tangent lines as we get closer to this point? Well, if I go out here pretty far away, I've got that upright positive slope tangent line. Right here, closer, I'm getting even more upright. Here, closer, I'm getting even more upright. If I do this on the other side, very similar. This would be a negative slope, but now as I get closer, it's an even sharper negative slope, closer, even sharper negative slope. So technically, by the time I get to the point, I would have this vertical line would be the tangent line. And what do we know about slopes of tangent lines? Slopes of vertical lines. A horizontal line, rise over run, does not have rise, has run, so 0 over something would give me 0, but vertical lines have all rise and have no run. So now I'm getting a number divided by 0, so for vertical lines, the slope is undefined. We could talk about the slope goes to infinity in some way, but as a function, infinity is not a legit answer. So if you tried to find the slope at this point, you would get undefined, no solution, and that's leading to a spot where the graph has a sharp point, spot where the function is not differentiable. So here we are not differentiable at x is -1, +1, 3, and 4. So coming back here, where is it differentiable? Everywhere else. So I'd start from negative infinity up to -1, but not including. Again, that's the point that is not differentiable. And then I would go from -1 to 1, and then from 1 to 3, and then from 3 to 4, and then from 4 to infinity. Just like continuity, everybody. After you do this once or twice, people can kind of skip over this and just they know what they're looking for. It is smooth here, but not here. So all these x's, it's differentiable. Then we've got a smooth piece here, but then we've got a jump. So we're differentiable on this interval. Smooth here, then an open hole. So differentiable on this interval. It's a small little piece, but this is still smooth. So differentiable here, and then smooth for the entire rest of the gap, this last interval here. So that's the first very big thing. What does it mean to be differentiable? That's what we're talking about. That differentiability for your original function is all about talking about a graphing property. Does f prime exist? Well, if we look at the graph, we can know by, as we said, looking for the spots that are not the breaks, the gaps, or the sharp points. Okay, second thing, second piece. Now that we have f prime established as a function, we have to realize we could always play this game and relabel. So that if f of x is my original function, f prime is the first derivative, but it is a function. So I could look at this, instead of looking at the inputs and outputs, and the outputs here are giving me the slopes of the tangent lines to this curve, I could just look at this as another original function. An original function that has a graph, that has x and y pairs. Again, the y's here really represent the slopes here, but we could just look at those as x, y pairs. So does it make sense to take another derivative? Yes, it does. And now, notice this is the first time I've started to use that notation, the first derivative, and it's because there are more than one derivatives. That if I take the derivative of g, that would have notation g prime, but the first derivative of g would actually be the second derivative of f. How do you get the second derivative? Well, there's no shortcuts here. You can't jump from f to f double prime. I'm sorry, that's the notation first thing. We use this little prime for the first derivative, a double prime for the second derivative. This doesn't stop. I can keep going. I could take another derivative here. I could use more letters, call this an original function, but we don't need to do that anymore. We just realize that there are more derivatives. What are these derivatives doing? We'll get to that. We've got a lot more. How do these derivatives, what does this tell me about the original function? What does the third derivative tell me about the original function? The fourth, I mean, this can keep going on and on and on. We can keep getting more and more derivatives. Honestly, we're not going to go much past the second. We'll occasionally maybe touch the third, but this could technically just keep going on and on. So we'll get to how those connect, but that's just our first thing to realize. That we're not limited to just one derivative, that we could keep going with this derivative process and get more derivative functions. And this is technically, some people refer to this as Newton's notation. Isaac Newton, one of the founders, whether you say calculus is invented or discovered, that's just an interesting conversation for a separate time. But Isaac Newton is one of the first people to really get involved with this. That's a very whole interesting calculus discovery story. Maybe we'll get to that at a different point. But anyway, this notation is named after him, and this is what he used. But there is, oh, and by the way, if it's f, f prime, f double prime, f triple prime. If it's g, g prime, g double prime, g triple prime, and so on. If it's a prime, a double prime. The letter for the function doesn't matter. It's the prime notation that we're setting up here. So this technically would go the same way. You could use y as the original function, then y prime, y double prime, y triple prime. When you start going past the third derivative, some people go to Roman numerals. Others start putting a number, but they use parentheses to make it clear it's not an exponent. So there's a little bits, but again, we're really never going to go that far. But this is a very, very common form of notation, so this would be the fourth derivative. But we also have to talk about Leibniz notation. Leibniz, he was a German mathematician who was actually working in France. And they did not work together, but they are often kind of given co-credit as the creators, discoverers of calculus. Again, whole interesting story behind that. But for right now, just the notation. He would still have your y as your original function, but then he would use dy over dx is his notation for the first derivative. That literally stands for the derivative of y, but it also includes this little extra with respect to x. And again, something else we're not going to see for a little bit. We'll come back to this. What's the big deal with this whole thing, respect to x? And we'll try and see what that means and get some better understanding. But that's just, again, just to get some notation out for now. So find dy dx, find f prime, still saying the same thing. Saying this will have some other context. Well, this notation will be better, will be more helpful for us than this notation. But again, for right now, just to establish that notation. For him, the second derivative would be written like this. The 2's, they're kind of like exponents, but just notice on the top line, it's going between the d and the y, and on the bottom, it's after the x. This would be the second derivative of y with respect to x. You could do the third. And this one, we're already just using numbers. The fourth, the fifth, the sixth, whatever, that's where that number would go. And as we were saying at the beginning, there's no shortcuts. If you want the second derivative and you have the original function, you got to start by getting the first derivative and then take another whole derivative to get to the second. So that's the second part of this notation. Just when you see d over dx, that's not the final notation for the answer. That's just the notation that's telling us take the derivative of whatever is inside the parentheses. Again, technically it's telling me take the derivative of this with respect to x. But again, for right now, just more notation for find the derivative. When we get into our next section, 2.3, we're going to learn a lot of shortcuts. So for some of you who are getting a little worried, thinking about that definition of the derivative and thinking, oh my goodness, am I really going to be using that definition 3 times to get down to the fourth derivative, or 3 times to get to the third derivative, or 2 times to get to the second? We're not going to, everybody. We're going to learn shortcuts. 2.3 is going to be a huge section that gets into all these different shortcuts that are going to be absolutely essential for us to learn. But again, we'll get there when we get there. We've got 2 more things left to say in this video. Started with the idea of being the concept of differentiability, the graphing property of f being differentiable, getting a little bit deeper into the notation, introducing the higher order derivatives that exists as a concept. And now we've got 2 more last things to finish up. Number 1 is that if we have a sketch of f, actually I'm going to go back and do this right here. Let's go back to this function, and I already asked you where is g differentiable, but in my second part, I'm going to have a second problem. Let's sketch the graph for g prime of x. I think the book goes a little bit further with this right now than I would like. I think we'll get more skills added that'll make this section a little bit easier, but it is a good place to bring this up. If you have the original, we can sketch the derivative. And the way we are going to do this is we are going to look for a couple of very specific values. We're going to look, it's not a specific x, y, or anything that we're looking for, but we are going to look for spots like these 2. This spot right here and this spot right here. What do you know about the derivative at those x coordinates? So let me actually put a little scale on here. So that'll be -1, and the second one will be x is +2. So what can you say about the derivative at those x coordinates? G prime of 1, -1, and g prime of 2. Well, the derivative, it's the slope of the tangent line. And what happens at these 2 spots? Why are these so special? Well, if you draw your tangent lines, what do you notice? Hopefully we're noticing that these are both horizontal lines, and horizontal lines Up here, we noted how vertical lines, their slope is undefined. And while I made that point, I noted horizontal lines have a slope of 0. So why are these such important points? When you go to sketch the graph of the derivative, basically what we're looking for in this sketch is where does the function touch the x-axis, and where is it above the x-axis, and where is it below the x-axis? Well, this is going to be the first key. Having these two tangent lines with a slope of 0 on the derivative graph, those become x-intercepts. The y value on this graph comes from the slope of the tangent line on this graph. Okay, that's definitely something. This is what I was saying before, why you can't just say it. The x-intercepts here and the horizontal tangent lines here, you need to be clear. The horizontal tangent lines on the original coincide with the x-intercepts on the derivative. And that could go vice versa. Again, that's what I mean later on. We'll start doing this the other way. You'll have this original sketch, and you'll have to realize that these points will go with these relative flat spots, these transitional points. This is a peak, this is a valley, and we'll see a lot more with those. Okay, so that's the beginning. That gives me the places where my derivative graph touches the x-axis, but how do I know the rest of the graph? Where is it above? Where is it below? Think of the signs of the slopes outside of these 2 points. Draw a tangent line. Doesn't really matter where you draw it. If you draw it here or if you draw it here, they both have positive slopes. And then go in between these 2 points, draw your tangent line here, draw your tangent line here, whatever. These have negative slopes. Go out here, draw your tangent lines. These have positive slopes. Positive slopes lead to positive y's. Negative slopes will lead to negative y's here. Positive slopes back to positive y's. And that's it, everybody. It's a sketch. I would never expect any more detail than that. These have positive tangent lines, positive slope tangent lines, so the graph is above the x-axis for those x values. A horizontal tangent line, slope is 0, so this had a y of 0. Tangent lines have negative slopes, so now my slopes have to be negative. How down do I go? Notice again, no y scale here, just whether I'm above or below. I am going to have to come back up and touch this. If you notice, the closer you get here, these will become less negative as they're getting closer and closer to flattening out. So this will come back up and touch. So I basically just did a whole big negative loop for this spots where all the tangent lines had negative slopes. And now I've got one more positive loop. That's it. That's all there is to sketching the derivative. Now, this is certainly a nicer example, just on the bottom corner here, just to point out, if your original function had a sharp point like this, actually, let me do it the other way. Let me make the sharp point going down this time. Instead of being a peak like it was here, let's make it a valley point. But it's not going to make much difference. If that's your original, this point, whatever this x-coordinate A is, on your derivative at that x-coordinate A, you'd end up with a vertical asymptote. Here, the tangent lines before A have negative slopes, so your derivative graph would be down here approaching the asymptote on this side. And on the other side of this sharp point, you have positive slope tangent lines. So you'd have an asymptote that does something like this. I mean, we can keep going. You know, if you've got a discontinuity like this, how do you draw the derivative? It's going to be a jump. A jump here would lead to a jump because we'd have to think about slopes here and then pick up with slopes here. And it's so likely there's going to be a jump somewhere. Here we're going to still have a hole in our graph. So notice now, after all that initial work where we had to focus on all these weird spots, now that we're really getting deep into calculus and we're establishing the derivative, now we go back to a lot more of what's common. So again, that's a lot more common. That's something you should definitely be able to do. Should be able to handle a sharp point a little bit, but again, we'll get a lot more practice with this. Okay. last thing for this video. Back to the word problems, everybody. We keep establishing the derivative as the slope of the tangent line, but we also need to establish in any word problem, in any application, the derivative is the instantaneous rate of change of y with respect to x. So we're also getting our units here as I say that. We've made that point several times, but now let's get a little further. I'm not going to draw any graphs to go with this, but just to get, again, some more words here. If C of t represents the amount of clean water in gallons, we're going to need units for any application, over a period of time in hours, let's interpret C of 3 equals 1200 versus C prime of 3 equals negative 150. Well, first thing, units. If this function measures the amount of clean water, again, maybe we work in a large apartment building, maybe we work in a desert type area and we're trying to preserve the ecosystem, whatever, but we're measuring how much clean water we have in gallons over a period of time. This would say that after 3 hours have passed, whatever time we started the clock, if we started at noon, it's 3 p.m. If we started at 1, it's 4 o'clock. But 3 hours after we started, there are 1,200 gallons of clean water still available. Okay? After 3 hours, 1,200 gallons of clean water available. But C prime of 3, now we're looking at the derivative. The derivative has units y over x, or in this case, c over t. So right away, right here I could note that this should have units gallons here, but even if we just saw this notation, having this description, we should be able to fill all this information in. But over here, this would have units gallons per hour. And what is this telling us? It still has the t as 3, so we're still looking 3 hours after whatever experiment that we've started, whatever time that was. After 3 hours, this is not how much clean water we have left. This is the rate we are gaining or losing clean water. And even this negative sign, that indicates a sense of loss, a sense of decrease. So after 3 hours, we are losing or maybe using 150 gallons of water per hour. So does that mean 1 hour later we would have exactly 150 gallons less? No, that's average. If that continues exactly, that's the way it would. But in this exact moment, maybe 2 minutes after, we turn the water off. So now we're not losing it that quickly. Or maybe not only that, maybe we've started to filter some water, so now we got to add some back in. If this was a plus 150, then we would be gaining or receiving more water at a rate of 150 gallons per hour. But now, let's finish this video with just one more example. Let's do same C of t. I'll use that same notation. Again, a lot of applications, t instead of x, because often we're using time as the independent variable, as our input, and that the amount of clean water depends on how much time has passed. But now let's use c for, let's use this as a money. How much money is in the cash register? And this time let's use this over a period of days. Over time measured in days. Oh, and our units, we have to be clear, are we talking about millions of dollars? So if you say the y is 1, that really stands for 1 million. Let's do this in terms of 100, just to get practice. Money in the cash register in $100. So what does C of 2 equal 2,300? How would that be translated? After 2 days have passed, I'm sorry, 23. That's what I meant, 23. C of 2 equals 23. After 2 days have passed, there is $2,300 left, right? Sometimes we get a little scale. It's not always just gallons. Maybe it's 1,000 gallons or 100 gallons or $100 or $1 million. So again, here, after 2 days, there's $2,300 in the register. If I said C prime of 2 equals, let's say, 7.1, well, units, 7.1, hundreds of dollars per day. If we do that little translation, that's a little awkward to say 7.1 hundreds of dollars. That would be $710 per day. And again, that is not a total, that is a rate of change. This is positive. We're making money. More money is coming into the cash register, and it is coming into the register at this rate. So again, on average, we could basically say it looks like we're making about $700 a day, but maybe this was a really good point in the day, and the rest of the day slows down so that this number would go down. So again, it's nice in that moment. And that's where instantaneous versus average, we could always have those conversations. Sometimes instantaneous is absolutely necessary. Sometimes average would actually be a little more helpful. But the derivative always gives us that instantaneous, and it always is a rate of change, and it always has units y over x.